All right, in this lesson, the first one from online lesson 3, labor demand, we're going to look at the short run decision of the firm. And because capital, physical capital, and technology are fixed in the short run, the decision variable in the short run for the firm is how much labor to hire or how much labor to demand. Okay, so because everything but labor hours or number of laborers in the short run is fixed. Over the long run, everything is variable, right? In the short run, the market price is fixed, right? Here, the market price is $11. If a firm that competes in this market wants to sell in this market, it has to charge a price of 11, right? It's a price taker, not a price maker. It can't charge a price above 11 because it sells a commodity, a homogeneous good that other firms sell as well. So if you try to sell at a price above 11, you're going to sell 0 because people can buy that commodity, that homogeneous product from many different competitors, right? So you can't charge a price higher than 11. The firm's not going to charge a price lower than 11 because it can sell all it wants at the market price. So it's going to choose the price of 11, right? That's a lesson from microeconomic theory. Okay, now this is called the production function because over the long run, technology, capital, and labor all are adjustable, right? All three are adjustable over the long run. Now, this long-run production function can be written this way because t to the 0.5 power is square root t. K to the 0.5 power is the square root of k. So these are the same equation, right? The reason why I write it like this is because I want to highlight the idea that we're going to let labor change in the short run, but we want to calculate this part here, right? This is giving me the coefficient. Once we assume short run values for technology and capital, this is just going to be some number, right? Now in the short run, capital is assumed to be 256, capital K. I'm doing this in Desmos, by the way, right? Desmos.com. I find it to be a very useful tool. And then little t is assumed to be 4%. So maybe 4% of the knowledge available in the universe is known to mankind, right? And this company has 256 units of physical capital, all right? All right, so what we need to do now is we need to calculate the coefficient of square root of L. And one way you can do that is by doing 4 raised to the 0.5 power times 256 raised to the 0.5 power, right? So I can do that. 4 raised to, this raised to is shift 6, 0.5 times 256 raised to, again, is shift 6, 0.5. And we get 32. Another way to calculate that is to calculate the output. Or sorry, I'll just type square root SQRT. SQRT gives us the root symbol. And then I'm just going to type capital K, which is 256, times T, which is 4. And I get the same number, right? 32, right? Okay, so what I'm going to do now is I'm going to convert this into my short-run production function. The coefficient is 32, right? If I include times L under the root, I get this production function. See this? I get this production function here, right? I'm going to squeeze the y-axis a little bit. I'm going to put in, I don't know, 1,000, maybe 1,300. So I've squeezed the y-axis, the output axis, to make it look more like the one that's in my open math, right? Now, the next thing I want to do is if I want to calculate different values of output based on different values of labor, right? So in order to do these calculations, I'm going to get rid of this row 3, by the way. Right. And again, the square root of K times T is 32. So this is actually Q equal square root of 30, sorry, Q equal 32 times square root of L, right? I can do that right here. 32 times the square root of L. You see that? This red curve is identical to this black curve. So the cool thing about Desmos is it automatically plugs those values in when they're defined, right? If I come down here and I typed L equal 60, right? 60 here. So when L is 60 hours, when the firm demands 60 hours of labor, it will produce this much output. And we want to round it, right? We want to round it to 2 decimal places. So in order to round this to 2 decimal places, right? In order to round it to 2 decimal places, I'm going to look at the second and third one, right? Because that second number is 0, right? Because this is 0, this third number is 0 in the decimal. That 7 stays at 7, right? Oh, I'm going to change this down here too. Okay, so now what happens is what Myopa Math is plotting that point, right? When labor is 60 hours, when the firm is demanding 60 hours of labor, output is 247.87, right? Now, what happens when labor is 70? Output is higher, right? Output is greater. Output is greater to 67.73, right? So when labor is 70 hours, output is 267.73. What about when labor demanded is 80? Output is 286.22, right? If I round it. That 6 makes that a 2 there, right? So now the Myopa Math is plotting that point, right? 80 hours corresponds to 286.22 units of output for the firm, right? And finally, leisure is 90. When labor is 90, output is 303.578. That 8 makes that 7.8, right? Okay. When labor demand is 90 hours, output is 303.58. Now, the next thing we want to do is we're going to calculate the marginal product of labor. Marginal product of labor holds capital and technology constant. And then it wants to know, basically it's the slope of this curve up here, right? We want to verify that this curve is the marginal product of labor. And this curve, the height of this curve over labor hours demanded is the slope at points along this curve. So here the slope is really steep, right? The slope is really steep, which is why this curve is so tall here. Here the slope is gotten smaller, which is why the height of the curve here is so low. So to calculate the marginal product of labor in row 70 here, 70 hours of labor, what we have to do is we have to calculate the output change, right, over the change in labor. So when labor was 60 hours, right, output was 247.87, right? This ratio is the average product of labor, average. We want the marginal. So now when labor is 70 hours demanded, output at that level of demand is 267.73. So the change in output is this number, and change in labor is that number, right? And the marginal product of labor is 1.986. Well, maybe I need to round it to 2 decimal places. Yeah, I got to round it to 2 decimal places. Okay. So at 70 hours of labor, marginal product labor is 1.99. That's what this is graphing here. And what that means is the slope at 70 here, you can think of this as the slope, right? The slope at 70 is 1.91, right? Now, technically, mathematically, 1.91 is a slope between the blue point and the red point. This is what labor was. This is what labor demand is. At this level of labor demand, that is what our output is currently. At this level of labor demand, that is what our output was, right? So this 1.91 is the difference in the red and blue numbers here divided by the difference in those two numbers there, right? But we want to think about this number here as being the slope at this red dot, right? So we're gonna think of the slope of the red dot as being 1.91. It's gonna be really close to it, right? All right, what about the marginal revenue, the marginal product of labor for 80 hours of labor? So what I'm gonna do is I'm gonna delete the output that corresponds to 60 and the 60 hours. And then I'm going to type down here 80. And at 80, output was 286.22, right? 286.22. When hours demanded was 80. So now the marginal product labor is this value to 2 decimal places, so 1.85. Okay, so now we're going from 70 to 80. Output's going from 267.73 up to 286.22. This difference divided by that difference is this value 1.79. Another way you can think about that is at 80 hours of labor, the slope of the product equation, product graph, output graph is 1.79. So the slope at this point is going to be really close to 1.79, right? And then finally, we have the values for when labor is 90, right? And 80 and was 80, right? So when labor hours is 90, output is 303.58. When labor demand was 80, output was 286.22. And so when we round this to 2 decimal places, we get 1.74. Okay, so when we go from 80 to 90, output goes from 286.22 to 303.58. And the slope of this red dot here, is 1.69, right? Okay, so now what we want to do is we want to calculate the revenues, right? We want to calculate the revenues here. And the price, if you remember the price was what? The price was $11. Okay. Now, if I were to calculate just P times Q here, I'm multiplying the 11 times a number that is not rounded to 2 decimal places. So instead of doing that, what I want to do is I want to calculate a Q that has been rounded. So I'm going to do Q equal to, well, Q1. If you type Q1, it'll go Q subscript 1. Q subscript 1 is going to be the square or the rounded Q. All right, it's going to be the rounded Q, rounded to 2 decimal places. So now I'm rounding to 2 decimal places. So if I don't use rounded numbers, my revenue's that. But if I use rounded numbers, rounded outputs, there's a difference, isn't there? 3339.38 versus 3339.37, right? So I want to use rounded numbers. So my revenue is this value. Now, when I plug this in, whoops, sorry. I need to change L back to 60, right? I need to change L back to 60. So when labor demanded is 60, when labor demand is 60, revenue is 2726.57, right? Now, when I press enter, what's going to happen here is I'm going to multiply. Essentially, what's going to happen is this black curve is going to be squashed down to here. And the reason why that is because we're going to multiply all the quantities along this axis, along this curve. We're going to multiply every point along the curve here by the price of $11. So 0 times 11 is 0, right? We're going to multiply 286.22 by 11 to get the revenue. We're going to multiply 303.58 by 11 to get the new revenue when we can produce, when we demand 90 hours of labor, right? Same thing's going to go down here, right? We're going to multiply this 1.69 times 11, right? So this black curve is going to get smashed down here to the near the labor axis when I press enter here. Okay. So that's exactly what happened, right? The marginal product labor curve got pushed towards 0 because the height on the marginal product labor curve here times my price of 11 puts us up here, right? So these are parallel. These are parallel, right? So if I multiply this by 11, I'm up here, right? Same thing's going on here, right? This height here is 247.87, right? This height here, because labor demand is 60. So labor demand is 60. The height of the black curve is still 347.87, right? The height of the blue curve, by the way, on the other hand, is 2,726 times or 0.57, right? So this point here to this point, the difference in that is multiplying this height by 11 to get me there, right? So we're multiplying this by a factor. We're multiplying this height by a factor of 11 to get up here, right? So that's how that's working. And I got to put this value here as well. Okay, now I'm going to change the labor demand to 70. When I change the labor demand to 70, my output is 267.73, right? But I'm going to multiply that by 11, which is 2,945.03. Okay, so I've multiplied this by 11 here, right? To get this value. Okay, so now I'm moving up my revenue curve, right? I'm moving up my revenue curve. And then I got to do it for 80. So when I define my labor demand to 80, my output can be as high as 286.22, this value, right? Multiplying that by 11 is $3,148.42. When I press enter there, I'm still moving up my revenue curve, right? I'm moving up my revenue curve here. All right, the last one is where labor demand is 90, right? In my model, labor demand is 90. What is revenue? Well, first, output 2 decimal places, 303.58, right? And revenue, multiplying this by 11, means my revenue is $3,339.38. Okay. Now, this value of marginal product labor curve, value of marginal product labor, this curve represents the slope of this curve at different points in time, right? So the slope here is going to be very large, right? It's going to be very large. The slope out here is going to be closer to 0, right? And it's going to continue to get closer and closer to 0, right? So this will continue to fall, right? Continue to fall. Okay, so what is the slope of the value marginal product labor curve? What's the slope here, right? How do we calculate the slope? Well, we can take the derivative of this function, right? We take the derivative of it, and then we can plug 90 into that derivative, or we can just we can do like we did before. We can take the differences in revenue and divide them by the differences in labor for each pair of points here, right? So now when my labor was 70 or 60, when my labor was 60, what was my revenue? Well, when my labor was 60, my revenue was that, right? The thing I'm going to paste over the 286.22 is the revenue at 60 hours of labor demanded, right? The revenue at labor equal to 70. All right. Now we're talking revenues, right? The revenue at 70 is $2,945.03. The revenue at 60 hours of labor is $2,726.57, right? And so the value of marginal product of labor is their ratio right here, right? Yeah, you gotta be really careful when you're copy and pasting in Mountain Math. Okay. Oh, this has got to be 5. So the at 70 hours of labor demanded, at 70 hours of labor demanded, the value of marginal product labor is 21.85, which was this value here. That 21.85 is the slope of this revenue curve when we go from the blue dot to the red dot, because labor demand increased from 60 to 70. And while that was going on, revenue increased from $2,726.57 to $2,945.03. So this change divided by that change is 21.85. So mathematically speaking, technically speaking, this 2185 is a slope of the line segment from the blue dot to the red dot. In economics, we're going to interpret the slope at this red dot to be in 21.85, and they're going to be really close to each other. Okay. So what happens when we increase labor demand to 80? So now we're going to increase labor demand to 80. When we increase labor demand to 80, our output is 286.22. Our revenue is 3148, 3148.42. When labor is 80 hours, when labor is 80 hours, revenue is $3,148.42. When labor is 70 hours, revenue is $2,945.03, right? So this is the revenue when firms demand 70 hours of labor. This is the revenue when the firms demand 80 hours of revenue. And the ratio of those two changes is 20.34. 20.34. Okay, we got that right. 80 hours of labor demanded means the value of marginal product labor is 20.34. That 20.34 is the slope of the line segment from this blue dot to this red dot. And that's found by taking the difference in the heights, the revenues, that correspond to these labor hours demanded, 80 and 70. So this difference divided by that difference is the 2034, technically speaking. But in economics, we're going to interpret the slope of this red dot here to be in 20.34. Yep. And then finally, we have when labor demand is 90, our revenue was $3,339.38, right? So this now is 90, right? So this was 80. And when labor demand was 80, revenue of the firm was that. Whoops. It's really hard to copy and paste in my open math. Huh. I guess I gotta just type it in then. 3148.42. Okay. So it's this difference here divided by this difference, right? And I get 19.10. So at 90 hours of labor, the value of marginal product is 19.1. The 19.1 is the difference in these two values, the red and the blue value, divided by the difference in these two values. This difference is 10, right? So take this difference divided by basically 10, and we get this 19.1, right? In economics, we're going to think of the 19.1 as the slope of the dot, of the red dot, the slope on the curve at the red dot, okay? The firm hires labor and purchases physical capital from perfectly competitive labor markets. As such, the firm pays workers $20.32 per hour. And $4.06 per hour is for its physical capital. The firm's fixed expenses, variable expenses, and total expenses is what? So down here on row 9 of my Desmos sheet, I'm going to calculate the fixed expenses. Remember, capital's fixed in the short run. So we got the R, which equals 4.06, right, per hour. We got the wage, which is $20.32 an hour, right? The fixed expenses, I'll just call it F, equals R times K. Fixed expenses, R times K is $1,039.36. The variable expense is just the wage rate, which is 2032. Okay, just 2032 times L, right? Total expense is the fixed expense plus the variable expense, right? So I just this is going to be my intercept, right? My intercept is my fixed expense, and then my slope is the 2032. Okay. So there's my fixed expenses, variable expenses, and total expenses. Now, the slope of the total expense equals the marginal expense, right? The slope, this is just a line here, right? And the slope of this line is 2032. We can call that value the marginal expense. Okay. Now in our table down here, fixed expenses are all held constant at this value, right? My variable expenses depend on what labor demand is, right? So if I type V equal W times L, I'm going to get 1828. Why? Because the leisure or labor demand was 90, right? Labor was defined to be 90. 90 times my wage of 2032 is 1828.8, right? So I'm going to go back up here and I can plug this value. Well, let's start over. Let's start at 60 here for labor, right? I'm going to grab that, delete it. I'm going to put it down here. Okay, so when I plug 90 into this equation here, I get, well, let's start at 60. Okay, starting at 60 hours of labor, if I plug the 60 into here, then my variable expense is going to be this value. Okay. Now, if I increase my labor to 70, my variable expenses go up, right? My variable expenses go up to 1,422.4. Okay. Go to 80. My variable expenses continue to rise. And then 90. All right. The total expenses are just the sum of the two, right? We got to sum the two right here, right? So what I'm going to do is I'm going to change V to fixed or total expenses. Okay, so when I add the variable expenses to the fixed expenses, I get total expenses, right? And the total expenses when labor demand is 90 is this, right? So if I were to add this to that, I get this value here, right? So I guess I'm gonna head backwards. Okay. Then when labor demand is 80, total expenses are 2664.96. So again, that's just the sum of these two right here, right? When labor demand is 70, total expenses is this value. Again, it's just some of those two, right? And then when labor demand is 60, total expenses is that, right? Okay, cool. Awesome. Okay, now we're going to calculate the marginal expenses, right? To calculate the marginal expense, we do just like we did before, right? Instead of taking the difference in revenue, right, from what it was when labor demand was lower, instead of taking these differences here, right? Instead of taking those differences, we're going to take these differences and divide it by that difference, right? So when labor demand was 60, total expenses were that value, right? And this ratio here is average expenses, right? but we want the marginal expense. So now our leisure, if we go from 60 to 70 hours of leisure, right? This difference down here is 10, right? Then at 70 hours of labor, we're gonna have a total expense equal to $2,461.76, right? So our marginal expense is 2032. Now notice that is the same as the wage, right? That's the same as the wage. Right? Okay. Now let's try it again. Let's do it from 80, from 70 to 80, right? So again, at 70 hours of labor demand, we have that much in total expenses. At 80 hours of labor demand, we have that much in total expenses, right? And again, our marginal expense is 2032, right? Yeah. Copying and pasting again is tricky in math, right? Now, why is the marginal expense remaining constant? I'm going to show you in a second. Okay, when labor demand is 90, right? An increase from 80. At 80 hours of labor demand, we have expenses totaling $2,664.96, right? At 90, our total expenses is this right here, right? Again, our marginal expense is 2032. Why is that? Okay, the reason why that is because if I differentiate the total expense equation with respect to L, this number is gone. This is a constant. And what we're left with is 20.32 because the derivative of L with respect to L is L raised to the minus 0 power, right? So the derivative of a line is the slope of the line. Okay, so a calculus derivative of a line, if you differentiate a line with respect to the independent variable L in this case, that derivative is just the coefficient of that variable L. So it's 2032, right? All right, now we got to calculate the profits, right? So I'm going to get rid of this. I got my total expenses here when labor's 60. I'm going to define this. I'm going to get, let's see. I'm going to define this as capital R, revenue, right? So my revenue at labor, I'm going to move this down here. So here's my revenue. Here's my total expenses. Let's go back up here and just verify. When labor demand is 60, my revenue is $2,726.57, right? This value here. When my labor demand is 60 still, my total expenses are $2,258.56, right? So the profit is just the difference between revenue and total expenses, right? So my profit when labor demand is 60, my profit is $468.01, right? Okay. When labor demand is 70, my profit is $483.27. When my labor demand is 80, my profit is 43.46. When my labor demand is 90, my profit, my profit is 471.22. So it looks like my profit is rising, right? 468 to 43. Still kind of rising, 43. And then declines to 471.22, right? So the firm's profits are going to be maximized for some labor hours, probably between 70 and 90 somewhere, right? Okay. The following graphs are copies of the revenue and value margin of product of labor graph curves above, right? So these are copies of the graphs above without any points labeled on them, right? So no points labeled on them. To find the optimal hours of labor demand by the firm's total expense line must be graphed with the revenue curve. This is the revenue curve here, right? That's the revenue curve. We want to graph the total expense line with it, right? The total expense line is right here. The intercept plus the slope times L, right? It's a line. We're going to graph it in here, right? The firm's total expense is graph starts at the point that corresponds to 0, labor, right? So if labor is 0, total expenses is 1,039.36, right? The fixed cost. So if this is 0 right here, 0 times 20.32 is 0. So total expenses would be $1,039.36, right? Okay, hit enter. And down here, that's my fixed, that right there is my intercept of my total expenses curve. And what that says is when labor is 0, fixed expenses, put the height of this line at this red dot. That red dot corresponds to 1,000, a height of $1,039.36, right? Now, because the slope of the total expense equation is the marginal expense, or just 2032, right? The line rises from left to right from this red dot. It rises because the slope is positive, right? See my line here? It rises. Now, the difference, this blue curve is revenue, right? And this red line is total expenses. So if labor is 0, our revenue is 0, and our total expenses are $1,039.36. So our profit would be negative here, right? We'd have a negative profit there if labor is 0. At this quantity of labor, whatever that is, at this quantity of labor here, revenue equals total expenses. So we'd be breaking even there, right? Eventually, for larger amounts of labor, this blue curve continues to curve in while this line here continues to straight out. And so we have two break-even points with respect to labor. This point here, and then a point out here somewhere where the blue line re-intersects the red line, right? Because the red line is going up at a constant slope. The blue line is going up at a decreasing rate, right? So maybe the intersection point is right about here, right? All right. So that the difference in the blue curve and the red line, that vertical difference is the firm's profit. Now, profit reaches a maximum when the slope of the revenue curve equals the slope of total expense curve, which equals what? Well, the slope of the total expense curve again was 20.32, right? $20.32 per hour. Now, notice this draws a tangent line, a line that is just tangent to the blue curve. That line is also parallel to the red line, right? At this point of intersection here, revenue is 3048.43 and expenses total to $2,563.37. And notice that at this point here on the blue curve, this tangent line, this light gray line, right, is just tangent to this blue line. This light gray line and this red thick line are parallel, right? This height here equals this height here. So blue or green, gray and red are parallel. So this point must be the point that corresponds to the optimal amount of labor demand, 75, right? If we hire fewer than 75 hours of labor, we might be down here, right? And our profit is going to be smaller than it would have been up here, right? Profit is the largest when these 2 points coincide like this, right? So my profit is the difference between these two, right? And it reaches this maximum at 75 hours of labor, right? According to the above graph, firm revenue equals what? $3,048.43. Okay. Total expenses equals 2,563 and 36 cents. Profit is their difference, right? Profit is their difference. So the profit is $485.07. I did that in the wrong box again. Profit is 485.07. And the quantity of labor that maximizes firm profit equals 75. Now notice here, 75 here, right? 75 here is the value of labor where profits are maximized, right? At any other value of labor, profits start to diminish, right? At any labor above 75, the difference between these two is getting closer and closer and closer to zero. So on this side of 75, profits getting smaller. On the left side of 75, profits are getting smaller, right? Profits are being squeezed until we reach a break-even point, right? Now, substituting that value in the marginal product labor curve, if I plug 75 into this value of marginal product labor curve, right? The height would be at 2032, right? The height would be at 2032. Right? And that's not by mistake. That's not by coincidence, right? For a given level of labor demand, right? If labor demand were here, firm profits are maximized, right? At this point, if wages equal this value, right? If wages are even higher, then the quantity of labor demanded is going to be even lower, right? So this curve represents points where profit is maximized for a wage and labor demand, of which that combination of values is a point on this blue curve, right? Thus, the firm maximizes profit in the short run by increasing the hours of labor it hires until the value of marginal product of that labor just equals the wage rate it pays for labor, right? This right here ends up being the labor demand equation right here. So this right here is the firm's demand for labor. It's downward sloping. And the price of that labor is the wage, the hourly wage, right? The hourly wage per hour is the price of that demand, of that labor, right?